Standard deviation. Consider these two data sets. So we've got two different sets of data shown as a dot plot. Now note that both of them are perfectly symmetrical. So the mean would be 5 for this one. By symmetry again, the mean is 5 for this one, so we don't actually need to calculate there. The mode for this one, well, there's two modes. We've got 4 and we've got 6. The median, because of the symmetry, will be 5. For this one, 2 and 8 are the modes. The median, again, is 5 because of the symmetry. The range here is going to be 6, and the range here is going to be 6. Now let's think about the interquartile range. Both of these data sets have 12 pieces of data. So if we did 12 plus 1 divided by 2, so that's 13 over 2 is 6.5, so we want to be between the 6th and 7th pieces of data. So 1, 2, 3, 4, 5, 6. So the 6th piece of data is 4, and the 7th is a 6. So the median is 5, as we already established over there, but let's just put that on. And so 6 pieces of data, 6 plus 1 divided by 2 is 3.5. So 1, 2, 3, 4, so halfway between these, so it's going to be 3.5. Then 1, 2, 3, 4, so halfway between these at 6.5. So the interquartile range is 3. Doing the same over here, we've got 1, 2, 3, and the 4th piece of data is there, so that one's 2.5. And then 1, 2, 3, and the 4th one's there, so that one's 7.5. So the interquartile range is 5. So really the only differences that we can see here with these two data sets are the mode and the interquartile range. Many of the statistics are the same, as we've just noted, despite the fact we can see the data sets look quite different. The mode is of little use, as each set has two modes. Perhaps the interquartile range is the most helpful. Now think about what the interquartile range is. So if we think about set A, the middle 50% of the data there is spread out by 3. In set B, the middle 50% is spread out by 5. A new statistic called the standard deviation will also be different for these data sets. It measures the average deviation or distance of the scores from the mean, and that should be larger for this data set as the data is more of it is away from the mean than is the case here where it's packed around the mean. It is used to compare data sets. A small standard deviation tells you that the scores are closer to the mean than a larger standard deviation. Let's find it on the calculator. So let's bring in the calculator. And we have looked at this before, but we're doing it specifically here now. So let's go to the menu and statistics, and we'll just clear out anything that we have there. Just go edit and clear all. And let's put this first data set in. So what have we got there? We've got a 2. We've got 2 3s. And then we've got 3 4s. And then we've got 3 6s. We've got 2 7s. And we've got an 8. And then the second data set starts off with 2s, 3 of them. And then we've got 2 3s. And then we've got a 4. and then a 6, got 2 7s, and 3 8s. So, calc one variable. Now let's do it for the first data set first, which we know is in list 1. Frequencies are just 1. And the standard deviation is this one here, 1.83. So 1.83 for that one. And then we do it for the second one, where we put the data in list 2. And we can see that that is 2.45. Now before we move along here, I'm just going to calculate it again. Let's just do it for the first data set. The sigma and the S are both standard deviations, but in this course we use the sigma as the one we want. So we want the 1.83, not the 1.91. So let's just get rid of all the writing. So for set A, we had 1.83, and for set B we had, I believe it was 2.45, I can't quite remember. So the standard deviation of set B is larger because, and without filling all of this in, the data in set B is more spread out from the middle than the data in set A. So therefore the average distance from the middle for the data in set B is larger.